I'm Neil Farrow. I've been a controls engineer for about 20 years, and for the last 3 I've been working for this amazing sensor company called SensoPart, and that's where I learned about IO-Link. Talking the party line, it's universal, smart, and easy. It's universal, it's an open standard. Smart, it's digital communication to and from sensors. Easy, it uses standard configuration formats and methods. This is the agenda for the talk today. One of the reasons it seems like IO-Link is working so well is in the beginning they got the key stakeholders together. The IC manufacturer was key also because now if you want to make IO-Link products, they're reasonably priced. Some key benefits: it uses M12 connection, the two-way communication gets you more diagnostics, and you can load set points from the PLC to the sensor, and you don't have to make a switch where every sensor from this moment forward becomes IO-Link. You can mix and match IO-Link and traditional sensors. Here's some terms, and when I put this together, it struck me that everything is an evolution. It's just an improvement on what came before. And the revolution of IO-Link is all of these things came together in one place. So some key terms: OPC-UA is OLE for process control. Universal access is what we think it all means, but the name is actually unified architecture. This is just the latest iteration of a proven standard we know and love. IoT, the Internet of Things, is just connecting your doorbell and refrigerator to the internet, but the industrial Internet of Things is connecting your sensors to the cloud or to a local server. This is the last page of definitions. Some key ones are the IO device description file, the configuration file for your IO-Link sensor, like a GDS file for Profinet or an EDS file for Ethernet IP. This is a IEC standards. The IEC is kind of like the IEEE of Europe. Standard 61131 is actually for programmable controllers, and you may be familiar with Section 3 of the standard. For the past decade, PLC companies have been talking about how they can form to this standard because they have ladder and they have structured text. And Section 9 of the same standard is where we get single drop communications interface, which is marketed as IO-Link. At the end of 2017, there were more than 5 million IO-Link nodes out there in the world, so it's already arrived. And it's really thanks to PLC manufacturers. A couple of the big ones decided to start pushing it, and some sensor companies started to push it, and many people started making IO-Link masters. Ethernet IP has the ODVA. IO-Link has the IO-Link Consortium at io-link.com. And it's an organization to improve the standard, promote IO-Link, and improvements to IO-Link. Most automation companies and sensor companies and PLC manufacturers are members now, including SensoPart. To jump to the end, this is what an IO-Link system looks like. From the PLC, we talk your favorite field bus to an IO-Link master shown in gray in the middle. And then from that master to each sensor shown in orange, we have the IO-Link connection. So this is showing 4 separate little single drop Ethernets from the master to each sensor. Parts of an IO-Link system are obviously the PLC and the IO-Link master. You have usually M12 cables. These are the same cables we're using today. An IO-Link sensor or a traditional sensor. For the IO-Link sensor, you need the IODD file and a laptop to load it. And of course, you need to use your favorite field bus. There's this fear with various masters and sensors that there's going to be this huge compatibility matrix, which is not the case. You can use any PLC, and you can use any sensor, any vendor sensor, any IO-Link sensor, or any traditional sensor, and any master. No compatibility matrix. Some of you may have noticed the asterisk. The one on the PLC just means it's got to have a field bus, of course. No brick PLCs. On the sensor side, It's 24 volt sensors. If there's anyone still using 120 volt sensors, it's not part of the new standard. I mentioned you can mix and match IO-Link sensors from various vendors, and it uses the same M12, M8, or M5 cables. And the asterisks on the cables, from the master to the sensor, it's got to be 20 meters or less, but it can be unshielded, which are a lot less expensive. The specification didn't calls out discrete PNP for existing sensors. I did not see NPN anywhere in the specification, although you can buy NPN IO-Link masters. Similarly, I didn't see 4 to 20 milliamp or 0 to 10 volt as a requirement in the specification, but you can find some IO-Link masters that will have that. Although by the time we're done, hopefully when you buy an analog sensor, you're going to take advantage of all the great features IO-Link offers. So this is an M12 pinout for traditional sensors that some of us know and love. The 24 volt power and the common with the discrete output. On your IO-Link master, it's the same. You've got your plus and your common and your output to your PLC input, and it can be a traditional discrete, but if you plug in an IO-Link sensor, then the master will talk Ethernet. So this is a picture of a standard M12 cable, and this is a picture of an IO-Link cable. It's the same cable. Next, let's talk about machine wiring evolution briefly. So you can kind of imagine if you've got 8-pin connectors on some of your sensors, that going to a communication interface is going to save wiring. So this is a review. Traditional machine wiring, we went from the input card down to a terminal strip, from the terminal strip to the sensor. Every sensor needed its own hot and common wire landed, and it looked like this, which is kind of a mess, which is why we put covers on the panduits on the wireways. Your control panel would be wired and checked out before it shipped, but often this blue connection to your junction box would be done in the field, and then you need to land all these wires on the left on your terminal strip and on your junction box, and then check them out. Your sensors did have M12 connectors. That's nice. So the next evolution was wiring blocks, where you still have every individual conductor going back to your PLC. You still have this, but it adds M12 on your sensor cable, so it saves you some wiring there. Next, we have remote I/O block, like Allen Bradley's Armor block. You talk a field bus to the master, and that really saves a lot of wiring. Now we're at IO-Link, and with an IO-Link master, we already have this digital data coming in over our field bus, and IO-Link is just extending the digital data all the way down to the sensor on these 4 different Ethernet networks, these IO-Link networks. And this is why they say IO-Link goes the last meter. It goes all the way down to the sensor. The list price extra for IO-Link might be $50. It may be 50 cents for a sensor. It's hard to tell because the street price is no extra money for a sensor and very close to zero for the master because there is a bit of competition. A colleague did this cost analysis using this example. If you had 40 analog distance sensors, you'd need 5 analog input cards and shielded cable. So with IO-Link, you have unshielded cable. You run it to an IO-Link master, and then from there you talk your field bus to your PLC, no analog input module needed, and it's $3,000 versus $40,000. To wrap up what I've talked about so far, IO-Link is an Ethernet-based point-to-point protocol from the master to the sensor 2 ways. You can also save the configuration in the master. So when your sensor inevitably is crushed by a maintenance guy or someone arc welds on the machine and you need to replace the sensor, when you plug in the new sensor, the master will check what make it is, what model it is. Oh yeah, that was connected here, and it will reload all of the saved parameters. You don't need to try to find a maintenance manual or a drawing and hope that there hasn't been an improvement where these set points changed. That's really a time saver. You can picture a typical control system with your Ethernet on top, where your PLC saves data to your historian or a database or an MES system. And below that, you have your field bus. And what we're talking about now is extending that Ethernet all the way down to sensors. So we've got industrial Ethernet talking usually Ethernet-based field buses and Ethernet all the way down to the sensor. Next, we're going to cover some more details about IO-Link masters and IO-Link sensors. The masters come in many varieties, but they use standard M12, M8, or M5 connections. Many sensor companies have a configuration toy like this with USB in and IO-Link out, and that could be used to configure a sensor on the bench or configure a sensor for a spare part for your first IO-Link machine. Later on, we'll have a demo of these two devices highlighted here in red and blue. Your typical IO-Link master will have a field bus in and field bus out connector and a power in and out. Some companies actually now combine these into one connector where you've got power and communications in one cable. This particular master has 4 IO-Link sensor connectors. You could connect a traditional sensor there as well, and it's got 4 that are traditional sensor only. Typically, every sensor connector will be an IO-Link sensor. So this shows how you would daisy chain IO-Link masters. Some companies have sub-masters where you have one field bus node and then you have these sub-networks. Typically the sub-network's not field bus, it's typically proprietary, and typically these don't talk IO-Link. These are only traditional sensors. I don't have a problem with either one of those things, so it's just a good thing to be aware of. IO-Link masters come in other form factors. Since we're in North America, let's talk about this Allen Bradley .io IO-Link master. This can handle 4 IO-Link sensors, so you do have to land the wires on terminals. But on the left here you see a .io Ethernet IP rack. So you can mix and match IO-Link and traditional sensors, or this is a great way to just add your first IO-Link sensor to an existing machine. IO-Link masters are also available in like a DIN rail mount format with terminals, and this company actually sells more of their DIN rail mount than their IP67 IO-Link masters, which to me seems to say people are retrofitting existing machines more than they're designing new ones. Another reason you might want to use the DIN rail mount is if you need IP69, you could put it in an IP69K enclosure to get that rating. Most masters are only IP67. There are a few IP69K masters out there. And just to note, the base model compact logics can only have 4 network devices. So if you have one VFD on your existing machine, you can only add 3 Ethernet IP IO-Link masters to that. So just be aware of that when you're upgrading your machine. Next, we'll talk sensor evolution. From the proc switch to fiber optic through beam, we get better photo eyes, and now we're getting them smaller and smaller and adding IO-Link to them. In 1990, we had our procs we know and love with one output, and that was it, and that's all we need, and that's still great today. Sensors, even with an M12 5-pin, will use all 5. You'll have an extra output or an analog interdiscrete or a remote teach input. Or they have the 8-pin M12. You can have discrete inputs and outputs to, for example, change the configuration remotely, or have multiple distance set points or multiple colors taught depending on the sensor. We have distance sensors with 16 pins that have analog and many discrete I/O and talk serial RS422, RS485. Before we had the procs with the on-off and your photo eye with an on-off, and now you can get additional signals out of that, like a weak signal. If it's a photo eye, you could have multiple set points. You could remote teach, or you could select many different configurations remotely. Let's just talk about the traditional 4 to 20 milliamp. Typically, PLC inputs are 12-bit A to D converters, and most often sensors are 12-bit also. So you have a resolution of 4095. If you have a sensor with a 70-meter range and a 2-millimeter resolution, that sensor is capable of 35,000 different increments of distance, but with the analog to digital converter you only get 4,000. So that's why high performance analog sensors had to go to RS-45 or 422 to serial communications, so that the resolution wasn't lost just by using an analog input. So with IO-Link, you can take that distance data right into the PLC and preserve your resolution. I'm not knocking serial. It works great. But the issue many people have, this is a flowchart for writing serial communications in a PLC. You could make it simpler to just ask for the data and get it, but this includes checking for errors and quickly retrying to make it a robust program. Compare that to IO-Link. Once you configure it, your PLC register updates as if by magic, because it is. Again, with IO-Link, there's no analog input modules. You send digital data from your IO-Link master directly into your PLC register. So that's the end of the history lesson. This is a talk on IO-Link, remember? The IODD file, it's in XML format, which is just a standard format that's been around for a while that a lot of IT people know. It's an evolution. So when you load the IODD file, you want to keep the zip file. You don't have to uncompress it. Load the zip file directly, and that zip file contains an XML text file and an icon or two of the sensor, which when I saw this I thought it was kind of absurd to waste all that room with an icon, but it's not that much room. And when you're commissioning a big machine with multiple sensors, it's nice to see the sensor in the configuration tool. This is an example of XML. The color scan start here is going to be at a value or a byte of 71. The point of this slide is just that XML is something that machines can understand and people can understand. You don't have to know XML because your sensor company will provide you with a data sheet showing a memory map of everything in the sensor. This one in the lower left you can see has energy in red, green, and blue because it's a color sensor. This one's broken down into cyclic data at the top and then acyclic data and then events and commands at the bottom, which is part of the IO-Link specification. It calls out process data separately from service data and also includes events. Process data is sent every communication cycle, like the distance measured or part present or what the color is. It's about every 2.3 milliseconds typically right now. And the specification calls for faster speeds. And that's just a few bytes of information, whatever's needed for your sensor. Other information, your service data, does not get updated as quickly and can be a larger amount of data. So things like the configuration we talked about when you first plug a sensor into a master, it will check the make and model of that sensor. And then there are events. So the sensor could be configured to just spit out data when, for example, the distance is at the end of travel, or when the sensor's over temperature. So you have these terms in IO-Link, COM1, COM2, COM3. That's not your PC COM ports. It just refers to the speed. On the IODD files, we're not shipping a CD. You get one from the sensor manufacturer's website or IODD Finder. If you go to io-link.com or you Google IODD Finder, you've got all the IODD files from all your different manufacturers. So if you have a machine with sensors from different companies, you can find them all there. You do have to load the IODD file from your laptop, and typically you do that with the software provided by the maker of your particular IO-Link master. And for controls engineers out there cringing, I already have 35 programs on my laptop, I don't want another one. Many have a web server built in, so you just need an updated modern browser. Some PLC programming packages, depending on the master you're using, can also be used to download IODD files. Top 10. We talked about more accurate data for your analog sensors, and everyone says it helps reduce downtimes, but I've broken it up here into two. First, let's talk about out of the box. As soon as you use IO-Link, you can hot swap sensors and it'll preload the configuration, and that's a huge time saver. There are, of course, LEDs on the master so you could see how it's behaving, whether it's switched on or off. It might have a red light if there's a problem with a particular sensor. You can track down problems using the web browser in your IO-Link master to pinpoint which sensor is the problem. You can reduce downtime even more with some features that require some extra programming and configuration. So if you're a consultant or integrator, here's your opportunity for value added. Error messages have to be configured on the HMI. There may be some PLC programming. For example, the low signal strength warnings. Every IO-Link master keeps track of how long it's been powered up. Many also have how long each port has had a sensor attached. So that information could be used with a little programming for some extra diagnostics. So you could have an extra HMI screen for commissioning and for troubleshooting on a running machine. It helps with spare parts inventory. Configurable sensors can take the place of multiple fixed sensors. You could replace your existing analog sensor with a new IO-Link sensor that would still have an analog output, so you could use it in both places. IO-Link lets you have quick product changeover because you can send new set points from the PLC. I have seen machines with like 2 analog sensors next to it for 2 different products. And then imagine if you had to reconfigure both of those the old way. Just getting more data from the sensor to a controls engineer seems like an inherently amazing and wonderful thing. And all sensors are similar. Once you've used one IO-Link master with one IO-Link sensor, you've got a feel for them all. And you can use your favorite PLC with your favorite field bus and your favorite new improved IO-Link sensor. Or use your traditional sensors and just add IO-Link where it makes sense. We covered fewer wiring connections. The last thing, you can, with some IO-Link masters, save data directly from the sensor to a database. You can do some HMI screens, diagnostic screens, talking to the sensor without going to the PLC for things like predictive maintenance, additional warnings, historical trends, SPC, statistical process control, predictive maintenance. Next, we'll show an example of loading an IODD file with a web browser. All right, let's go over how to load an IODD file into an IO-Link master, and you can decide if it's easy. I've got a SensoPart FT55CM color metal sensor connected to port 1 of a Comtrol IO-Link master. In the browser, just type the IP address of the IO-Link master to open up its web page and click on Attached Devices. Then Upload File, and then choose File. From the dialog box, we want to pick the CM with a 5-pin connector. And then click the Upload button. Notice that was in a zip format. The zip file includes the XML text file and a picture and icon of the sensor. Now we go to Config, and on port 1, we're going to click Edit. These are all the parameters about port 1. We'll edit, and I have something in there, so we have to clear it first. We'll click the Clear button, Continue. All right, now port 1's cleared. We can click Get Attached and save it. Okay, now let's look at it. We click on Attached Devices and see if it identified it correctly. We'll go to port 1, and it's updating the vendor name, and there's the new part number. So that's pretty straightforward. Next, we'll look at a real-time trend using the configuration toy. We're using SensoPart's proprietary demonstration software and a USB to IO-Link configuration toy. You could use an HMI package with OPC-UA to talk to a traditional IO-Link master you might put on a machine to do the same thing. We have 3 samples of plastic that are very close in color. They look the same in the office. If you move them into sunlight, you can see that they're actually like brown and black and blue. Okay, here's our first part. We'll test, and we'll look at the trend. We'll click Continue, and
capture some data and click Stop. And you can see red, green, and blue, and at the bottom the black is brightness. Now we'll switch to the next part. Again, we'll capture some data, continue, and stop. And you can see this one has less blue and less red. Now we'll switch to the next part. So we click Continue to capture more data. And then we click Stop. Now we'll switch to the next part. This last one we're teaching is actually the background, which is important for color applications. And the point of this whole thing is just we're using IO-Link to directly capture processed data. You can go through the PLC or you can skip the PLC. You can go right to your historian, right to your HMI's real-time trend, or right to the cloud.
So hopefully by now you have an idea of the capabilities of IO-Link, how you can put it in your existing machine for improvements, and how you'd plan a system for your new machines. Here's a list of some resources I'd use when I put this together, and I just want to leave you with a pseudo quote from Warren Miller. If you don't use IO-Link this year, you'll just be a year older when you do.